Good day, students. Welcome to uh, a video clip on related rates. We're going to be focusing on spheres this time. So let's consider the problem. It says a sphere is being inflated at 10 feet cubed per second. How fast is the radius increasing once the radius is 4 feet? So let's see if we can identify some components here. This clearly right here is the radius, right? So this is at a spot in time. Um, this figure right here represents a radius, right? How about this 10 feet per 10 feet cubed per second? Well, what is the dimension of volume? It's cube, right? Remember, cube is volume, square is area, and just uh, a linear or degree 1 is basically length. All right, so this one is raised to the first power is just like a length, like radius. This is raised to the second power. Length raised to the first power is like a length, and then length raised to the second power is the area, and then length raised to the third power is a cube. So if you look at this 10 feet per second cube, the fact that you have a cube here, that's volume, and the unit of time is second, right? Second is the unit of time. So this piece right here, we know, is going to simply be the change in volume. So it's basically dV dt. All right, so just by looking at the units, you can basically guess what each component means. All right, so what I'm going to do, let's make ourselves a sketch of the scenario, and then we're going to see how we can solve the problem. All right, so we have a circle um, with a specific radius. I can make this fit. But what's going on here is this sphere is like a balloon, right? And it's constantly being inflated. So as air is being pumped into this balloon, the volume is changing because it's getting bigger, and the radius is changing because uh, the whole sphere is getting wider. All right. So uh, basically, here goes your radius r. That keeps changing, and then the whole volume keeps changing as air gets pumped into it. All right. So what is the formula that relates to volume and the radius? Is the volume of a sphere formula, right? So what is the volume of a sphere formula? Think back to geometry. The volume of a sphere is given by 4/3 pi r cubed. All right, this is an easy problem because you just have two variables and you don't have to express a third variable in terms of another. So this is a really nice problem. All right, so now we need to use, this is the formula that we're going to use to generate the related rates equation. So when we generate the related rates equation, we'll plug in what the information we're given, and then we'll find what we have to find, okay? So it is ask how fast the radius is increasing. So how fast the radius is increasing is basically changing radius per unit time, which is the RDT. That's what we're going to be looking for, okay? All right, so let's differentiate this equation, the volume equation first, and then we will generate our related rates equation and then see what we need to do. Okay, so to differentiate this, remember v is to the first power, and I'm differentiating both sides with respect to time. So let me write it like this: d dt of v, which is volume to the first power, equals d dt, which is derivative with respect to time, of 4/3 of pi r cubed. Okay. All right. So this is like implicit differentiation. So when you differentiate this, v to the first power is like a constant rule. Since there's one here, it's just like one, so it's going to be 1 times v to the 0. So it's going to be 1. The derivative of v is 1 times dv dt, because we're doing the chain rule here, equals, now since you have a constant, 4/3 and pi are constants, we factor them out first, 4/3 pi, and we're going to be differentiating r to the third. All right. So the left side, 1 times dv dt just stays dv dt. And then on the right side, the constants remains unchanged. I'm going to apply the power rule to differentiate this. So what's the power rule for r to the third? It's going to be 3r squared. And then using the chain rule to differentiate r, dr dt. Okay, just as we did on the right side. Okay, so let's simplify this a little bit. We're going to have dv dt equals, you notice that this 3 right here, and this 3 can reduce. 3 goes here 1, 3 goes here 1. So you're going to have 4 pi r squared dr dt. Okay? Now, what I can do is I can plug in what I know and find what I need, and then solve for what I need, or I can solve for dr dt and then go on from there. So let me just plug in what I've been given, okay? So dv dt is a change in volume. If we go back to the question, we notice that the volume is changing at 10 feet per second cubed. So dv dt is 10 feet cubed per second. It's positive because it's getting bigger. The r dt, what is on earth is the r dt? The rate at which the volume is, at which the radius is increasing, right? The r dt, we have no idea what it is. That's what we're looking for, okay? But we're looking for the r dt at a particular point in time. That is when the radius is what? When the radius is 4 feet, okay? So we're going to plug in all these pieces of information into this, and then we're going to solve for the r dt. So I'm going to leave out the units. When we're done, we'll talk about units, all right? So dv dt is 10 equals 4 pi. R is 4, right? So we're going to be squaring that. 4 squared dr dt. Okay? So this becomes 10 equals 4 squared is 16. 16 times 4 is 64 pi dr dt. And then we're going to divide both sides by 64 pi. So divide this by 64 pi. Divide that by 64 pi. And then your final answer is going to be, using the reflexive property of equality, dr dt equals 10 over 64 pi. Okay? But we know that these are even numbers, so we can reduce it, divide by 2, right? So dr dt can be further reduced into 5 over 32 pi. Okay, so what's the unit of this measure? Radius is length. In this case, we're dealing with feet. And the measure of time that we're dealing with in this case is second. Okay? So if you want to write down what this answer means, the meaning of this answer is that when the radius of the sphere is, what is it for? Is 4 feet. The radius is increasing at 5 over 32 pi feet per second at that point in time. Okay? So there goes your answer. Thank you so much for paying attention to this presentation. Please subscribe to my videos so you can get updates to more cool problems like this. And do feel free to share this video with your friends via Facebook and Twitter or Google+. More videos you can find at math.serve.com. Thanks again and have a wonderful day.